Hello and welcome to the next episode of the Klingberg Wing Mark II development. I'm Raul Klingberg, your host. Today you see I'm in the cockpit and we're going to have an interesting discussion that crosses over a couple of different worlds, an engineering world and more an intuitive human world, and that's the integration of human to machine. And it's a very interesting topic. I hope you stick with me and watch the rest of the video. So come on along. Okay, glad to see you're still here. We're going to talk about integrating humans with machines. It's a arcane topic, really. It's a whole profession. You can get degrees in it, certify yourself in it, and spend your entire life working just in that field. It used to be a lot of guesswork. It's becoming more of a science. There are programs now where you can do a decent simulation of the spectrum of humans that you can expect to interface with your machine and how they fit into the scenario. And that's the key to it. Mostly it's about fitting. How far can they reach? How tall are they? How can they bend? And that is a key part of the problem. Another part of the problem that is not so easy to predict or write code for is how human beings behave. Human beings do the most unexpected things at the worst possible time. And we have to try to design vehicles to avoid catastrophic ends when human beings do something unusual. So I'm going to talk today a bit about some of the human factors that cropped up while I was working on the cockpit for my new glider and are still cropping up, and I'm having to work with them on a day-by-day basis. So the first thing that I'm going to talk about is the height of the pilot's cage relative to where the pilot's suspended and relative to the harnessing system, how it's all set up. And I'm going to pull my feet back here for a second so I can set them on the ground and talk a little bit more clearly about what's going on here. My wing's a little bit different than anything else that's been out there before. About the closest vehicle would be the Swift, but the big difference between the Swift and my glider is on the Swift, the pilot is suspended from essentially the side rails of the cockpit. And when the pilot's actually well below the side rails, when they launch, the rails are way up here under their armpits. And once they're up flying, the pilot's well below the pilot's cage. And they have a strap here that runs over a ratchet pulley up front. And the pilot pulls the strap and literally jacks himself up into the cockpit. An interesting and novel solution to the problem, because how often do you think about, okay, I'm going to have to insert my pilot into the cockpit after I take off? That's a pretty unusual scenario, yet that system works quite well. On the downside, when I've looked at the components of that system, it looks heavy. Okay, now that the leaf blowing is over, we're back to things that are much more fun to talk about, like airplanes, gliders. So here we are in my cockpit, and I was discussing the pilot suspension system and how, unlike the Swift, I am suspended from the wing itself. You can see that I am free to move fore and aft, and if I want a little bit side to side like this. Now the side to side is not going to gain me much in terms of any roll control, but in terms of pitch, I can have quite an impact on the situation. I can move the CG significantly. And in fact, for flying wings, moving the CG forward is a big plus when you want to go fast. Rather than putting the stick down, elevons down to go fast, that causes a lot of drag at high speed. Much better if you just keep the elevons kind of in neutral and we bring the weight forward and we pick up speed that way. In addition, if you go see my other videos, I'll put a link in the description about pecking and pitch damping. And I can provide pitch damping with my body got my arm over here, and I can damp out the system because my weight is significant compared to the weight of the aircraft. So that's another plus. But there are some drawbacks. The Swift has a pretty easy system to deal with. You get strapped in, you're hooked to the pilot's cage here, and when you lift the glider up, the strapping system for lifting goes to the same place as where the pilot is hooked in, to these side rails. By doing that, they have two advantages. They have the advantage of you can make the hook-in points common and simplify the system, and you don't have this issue with getting the right proportions between the suspension system here for the pilot and how long are the lift straps and how big is the pilot's cage. That almost becomes a moot point. With this system, averaging those out or figuring them out so that they both work is very difficult. It's a matter of just a few inches here and there. One way you end up with a really big pilot's cage, larger than this one, and the other way you end up with a really short pilot's cage and you end up having to crouch over like this to launch it because you're up against the wing. Now, as I mentioned, the Swift has this system where they jack the pilot up into the wing, and I will put a link to a video that has a review of the Swift cockpit, and you see those components, you're going to see they look pretty heavy. Yeah, they're aluminum, they're fabric and so forth, but that's got to be adding at least 1.5 pounds to the weight of the aircraft, and that's 1.5 pounds we don't want. Plus, it violates my rule, my basic rule of aircraft parts. The very best part is one that doesn't exist. Because A, doesn't weigh anything, and B, it can never fail because it's not there. The more parts you add, the more complexity you add, it's the higher weight and higher probability of failure somewhere along the line. So if we can simplify, and get rid of parts, so much the better, especially if they're moving parts. Okay, so jacking the pilot into the cockpit is an answer. It's been proven to work well, but it does violate some of the other KISS principles of keep it simple, stupid. And let me tell you, the hardest thing in engineering that I've ever encountered is keeping things simple, because engineers are really smart. We have a lot of design tools at hand, and we can solve any problem. And we tend towards, well, I got to add this and this and this, and if I do this and this and this, and it solves the problem. And the next thing you know, you have a pretty complex solution on your hands. And then to whittle that back to the essence of what you need to do the job is difficult. So engineers are hard-pressed to sit there and go, I need to design something that's simple. I need fewer parts. I need simpler motions. I need no motions at all. And as you begin to restrict yourself on, I can't have this and I can't have that, the design solution becomes much more difficult. And I spend hours upon hours scratching my head going, how do I get rid of those parts? How do I do it simpler? And I try to do that work ahead of time before I build the aircraft. Sometimes I do it with mock-up work to avoid building it into the aircraft and trying to figure out how to take it out later, because it's very difficult to remove weight after the fact. See that when I stand up here, in order to lift the aircraft up like this, I have to hunch over a little. Now that hunching over is a compromise. I have to duck my head a little bit to launch. And that was a compromise so that the pilot's cage didn't have to be any bigger. So you got to run with this thing a little hunched over. And the other thing is, I didn't want wheels that were gigantic and heavy. These are relatively small wheels. I got a 20-incher in back. I think I got a 16-incher up front. And with my feet up, I want to be in a situation where my butt's not going to hit the ground if I have to land on the wheels. Wheels are not really meant for landing on, but it might be a case where you just can't get your feet down, you're just not ready, and you just got to set it down on the wheels. Or maybe it's been a really long flight and your legs are asleep, and you got to come in on the wheels. So these straps can't be too long. My butt cannot hang out the bottom of the cage too far. In addition, I don't want a bunch of my body sticking out the bottom, creating drag. Then I got to go build me some kind of complex, heavy cockpit fairing down here, close it in, some clamshell thing. Right now, my only intention is to have a small closure up front by my feet across the bottom. Feet go up inside like this on top of that enclosure. So my idea is to leave all of this open, and then eventually there'll be a fairing behind me, and there'll be a piece that comes forward up to about my butt, and the general flying position is more like this. I'll have a set of straps that come from the harness here, not the lift harness, but my other harness. Here we go. Set of straps that come from here and go up to the shackles where I'm hooked into the glider. And that'll give me a nice resting position, and I'll be supported, let's see, grab it here. I'll be supported like this. I'll be held up like this. I'll be very comfortable. Might put a headrest on here eventually. And I have a clear view straight up overhead, except for the tail boom, but I have a clear view of who might be flying in the thermal above me. I have a clear view straight ahead, all the sides, all the way around. Good view. The only view I don't have is up this way, but if I push back and look, I can see that area generally. So it's always a compromise on the viewing angles, and you do the best compromise you can get. There are worse situations. Now, with the Swift, what they have is their wing is designed differently. There's less taper in it. When you have less taper, your aerodynamic center ends up further outboard on each panel, and that means you can place the pilot further aft. And their pilot is actually placed pretty much at the trailing edge here, and they don't use a tail boom, and they have a trailing edge that you can open up. And if you go look at the video, there's a canopy there that opens up. It's zippered in the middle, and when the pilot stands up, his head actually sticks up above the wing. The pilot's cage is much shorter. So when he runs to launch, his head is up where the wing would be, and then after he's up, you can zipper close the canopy. Another situation there is they got more moving parts, you got a zipper, you got a pull cord, you got pulleys. It's more complexity. But it helps solve some of their how do you pick it up and run with it issue. So the whole situation is a bunch of factors moving at once that you have to adjust each one a little bit here and there until you have something that works. It's very difficult to predict ahead of time. Some people might wonder, why don't you just get a CAD system, put a human figure in it, put your controls in it, and figure it all out on the board, and then just go build it. Sorry if we're picking up the leaf blower noise across the street. I'd like to get the video done, so we're just going to move ahead, and I'll speak louder over the leaf blower, because apparently it's leaf blowing day across the street. Even though it's a really windy day here today, and any leaves they blow are just going to blow back. But that's neither here nor there. So let's see, back to where I was. Where the heck was I? Mock-ups and CAD models. My buddy Bob always gives me a hard time about CAD models and not working all this stuff out ahead of time. And I'd rather just build a mock-up, or in the about amount of time that the days and days and days I would spend drawing it up in SolidWorks, I can actually build the cockpit and put in parts and see what works. And if they don't work, I cut them loose and I move them somewhere else. And as a matter of fact, that's what I've actually done with this cockpit. I built a very simple mock-up, did a little bit of work with it, really didn't know how I was going to solve all the control placement and control functions, and I spent quite a bit of time thinking about it. I didn't have a good solution, and I figured, well, something will come to me. I'll figure it out before I finish the glider, and that's essentially what I've done. For example, I'll give you a quick example. I thought for sure it was going to be a push rod system from the gearbox up to the wing and hook into the drive system up there, such that when you plug the wings in, the controls would already be hooked up. Let me tell you, that design, no matter how you did it, was really heavy, complex, with a lot of moving parts. I did not like that at all. Just too much room for failure, too much complexity. The Swift has push rods. Their push rods can stay in place because of how their cockpit is set up. It stays together. This is a parallelogram. This whole thing folds flat up to the wing. So that means the push rods would have to come out. So I got to have some way to reach up inside the wing and pin it to the control horns there. I got to hook it up down here. A nightmare. So I ended up with, there's not much that's lighter than cables. Cables are really incredibly light for what they do. So I have a system here. You can't see it up here, but there's a couple of holes up here where we shove the cables in. They come out here, the bottom of the wing, and down here they go. So when we put the wing on, we stuff the cables in, down they go. little clevis pin, 4 connections, controls are hooked up. And there are no torque tubes to fail, there's no bearings to fail or bind, and there's a whole bunch of fewer parts that need to be put together. And it's somewhat similar to what I had on my first wing, slightly different setup, but similar enough that I know it works, and it's lightweight, it's simple, and it reduces the probability of failure of any given component. So better to go with a known answer that I know is a good solution before rather than create something new that's more complex. Just for the benefit of being able to stick the wings on without having to hook up any other connections for the controls. Okay, so now we have a solution that's cable-based. And the gearbox is pretty much the same as I used on my first wing. Control stick is set up the same way. I got a nice file handle here that I drilled out and put on the control stick. And there's the push rod that goes forward to run the side gear that is for elevator. And then we got the standard aileron movement. And when I did the cockpit mock-up, I set up one of these and I went, oh, look at that. That works pretty good. I can have it over to the side. And I keep myself out of the way of it, and it'll be good. Well, that's where I went wrong. Just learned as we went forward here that this is going to be a bit of a problem. You're saying, hey, I thought you already went out and did ground testing, and didn't you find the problem then? And really the problem only shows up when you have the suspension harness on and the lift harness and you're up in the cockpit. And let me show you what it is here. Okay, so once I get my feet up in here, and now you see the problem. The push rod for the elevator runs into my leg. Unless I'm sitting over here on the side, there just isn't room. Cage could have been wider, could have been 30 inches wide. That'd probably been better. But, well, it's too late now. So in for a penny, in for a pound, I got to fix this one. Can I move the stick over? No, the control horns will hit the cage. I could mount the stick up higher, put this up higher so it would clear here. Oh, but then I have a cable in the way that's holding the pilot's cage together. So moving it up isn't much of an answer. So what I'm going to have to do here is I will have to move this push rod. The elevator push rod is going to have to move from the bottom here to up here, and this control horn will have to flip around 180 degrees, and I'm going to have to drive that control horn on top, and that'll put the push rod up here where it will generally be out of the way, or at least I can stay out of the way, and I'll have a little less leverage on the stick. So this stick might have to be a little bit longer, but we'll find out in the future. But at least I need to modify this for extended flights where my feet are retracted. For the first few hops, probably okay the way that it is now. Okay, let's get the feet back down. So if I'm flying along seated like this, holding on, well, I can keep myself over to the side. I'm pretty much out of the way here. And heaven forbid I need this much control when I'm on the first few little short hops. If I need, 45 or 50 degrees of stick deflection, I'm in trouble. Hopefully I'll only be a few feet off the ground if that happens. So the other main control that we have here is the flap handle, and that's right over here. It's just it's a convenient spot, and up and around and up into the wing it goes. It comes out over here on some side cables, control horns. You go watch the other videos to see how that works. The thing that we learned early on in the ground testing was this cleat that's over here. You probably can't see it. Let me see if I can get out of the way. This cleat here, I used to have an open cleat, and if you pulled the rope out, well, it fell forward, and the handle will be way up there where you can't reach it. You're like, oh, I can't reach the flap handle. Flap handle is kind of critical, not just for landing, but for maneuvering in flight. These flaps are actually used for pitch trim. You can go watch my other videos on that. So I had to install a captive cleat here where the rope can't fall out. Now that's the kind of thing that when you're working on a CAD model, you wouldn't think of in a million years. It's like, oh, yeah, it could fall out of there, it could fall forward. Oh, where can I reach? Oh, I can't reach that far. I got problems. And it's just, you're sitting at a bench, you're staring at a computer screen, you never think of that. Get in the cockpit, play with it once, it falls, and you go, uh-oh, I got a problem. And it takes about 5 minutes to find out what the true nature of the human-machine interface is, the reality of it. And then you can solve that problem. I put in a captive cleat. Now, here's another thing about keeping it simple. You could have a pulley here. You can mount a pulley on top of this cross member, The rope goes in, around the pulley, up it goes. Got to have a mount for the pulley. Got to have a pulley. Got to have bearings in the pulley. It's a standard system, but it's got more parts, more moving parts. I like simple. I said, hey, I got a tube that's round. Pulleys are round. Huh. This tube doesn't rotate though. Oh, I could slide a tube over it, and the tube over the tube could rotate, and I could build my cross tube into a pulley. I was a little late for that because it's all glued together already. And then it dawned on me, I says, this rope, this nylon rope, really slippery. I just need something slippery on the other surface. So what I did is I wrapped Teflon tape around this cross member. And it's not a solution that lasts for years and years and years, but, you know, most people don't fly in the wintertime. They got some weekends, they just cut this tape off, put new tape on. So all I needed was to create a couple of guides for the rope to make sure it didn't go this way or the other way. And it's very simple, a couple of graphite plates and a little piece of plywood to go around the curve. And there we go. That's the pulley. And this is really slippery, works great. And you know what? The bearing will never fail. The pulley will never bind. There's nothing in here for the rope to catch on. It's really simple, no moving parts, lightweight. And you know what? When I was designing the cockpit, when I did the cockpit mock-up, that never crossed my mind. Not once. What was in my mind was pulley, all of the way. In fact, I thought of two pulleys. Pulley here and a pulley up at the wing. And what turns out is I have guide tubes up in the wing. I have plastic tubes inside of aluminum tubing. Here's the aluminum tubing here, here's the plastic coming out. There's no pulley up there. It just slides through the plastic tubes, and the aluminum tubes provide a mounting system for the slippery plastic tubes. So within the whole flap system, the only thing that really moves is the rope and the control harness for the flaps. And the rest of it, no moving parts. And if we need to do maintenance, we got a little U-hook here, or a carabiner, a U-carabiner, and we could just unscrew that, disconnect the cables, and take the system apart. So simple, straightforward, and easy to maintain, lightweight. Now, another thing about human factors, it's really bad to distract the pilot. He needs to concentrate on flying. So you don't want a bunch of junk up here if you can avoid it. Blocks his view, distracts him, you know, and it's bad enough we start sticking instruments up here. Oh, you got GPS with a map. Oh, look at how far I've gone on the map. Oh, when you crash into somebody else in the thermal. So the fewer distractions, the better. So I've tried to keep the front view very clear. I'm using cables instead of struts. That's how I ended up with a tail boom. I didn't have a tail boom originally. This was going to be struts up here. But I really wanted to get all of that junk out of the pilot's view. And somewhere in here I might be able to, I'll try to put up a picture of what the forward view out of the Swift is. And you'll see what I'm trying to avoid. Not that they're a bad solution, it's just I'm trying to improve on a previous design. So that required a tail boom so that I could have opposing cables. Now these cables, front and rear, no different than a standard hang glider. We got a triangle bar, and we got cables that go to the nose and cables that go to a tail boom. So it's kind of a marrying of the two systems. Cables are very reliable, super strong for their weight. It's a really good answer. And a home builder can do cables on his own. You don't need to go out and have fancy aluminum fittings machine to fit in your struts. So that's why I'm on a cable solution. Clears up the view, keeps the clutter out of the way of the pilot. Some pilot wants to come in here and put in a whole instrument deck and distract himself. That's up to him. So let me get back in the position here. Normal flying position. So here we are. I got flaps over here on my left hand, which I can deploy easily. I got the stick here, and when I'm on tow, look, I just reach up. It's a natural reach position. You may not be able to see it in the video, but I got the release ball right here. Now that wasn't the first position for the release ball. It was over here and over there and then over there, and now it's here. And now it's in the right spot. So it took a few shots to figure it out, but okay, I'm flying right here, my hand's here. I can pull it and release, and when I'm flying normally, that's basically outside of my peripheral vision, and the dangling ball of the release is not going to annoy me or distract me. And I solved the pulley problem the same way that I did down here. I leveraged the no moving parts slippery tape, and I built a little round thing here You can't see the little fitting, and it bolts onto the pilot suspension system, and that is the 90-degree turn for the tow release pull knob. So very simple, few moving parts. One moving part, the rope, and that goes up to the release mechanism up front. So, and the rest of this is, I like to have a cockpit that's intimate, where you feel that you're integrated with the aircraft. When you achieve that feeling, um, I think it's easier to pilot the aircraft. If you're lost in the cockpit, or the cockpit is not amenable to how humans feel when they're in it, it's a harder aircraft to fly. I've flown dozens and dozens and dozens of different types of aircraft, and I've been in the good, the bad, and the ugly. Um, and you know, surprisingly, and I'll pull my feet back for this little story. Surprisingly, the largest aircraft, certainly the largest wood aircraft ever built, biggest wingspan, the Howard Hughes's H-1 Hercules, also known as the Spruce Goose, has an amazing cockpit. I'll put up a picture here. I was graced one day with the opportunity to go in the cockpit and sit down and see what it was like. And let me tell you, behind the pilot seat, that deck, the cockpit deck, is about the size of a ballroom. You could hold a huge party in there with dozens of people dancing around and having drinks. It's gigantic. And I was shocked by it. I stood there and I looked around and went, wow, it's huge. I mean, I've been in a 747 cockpit, sat down there. That cockpit doesn't hold a candle to the H-1. H-1 is just huge. Yet, I slipped into the seat, right where Howard Hughes sat when he flew it. Got to put on a simulated hat like his. And the first thing I realized was, it was probably one of the most intimate cockpits I'd ever been in. It's not simple by any means. There's a load of controls, but they're all within arm's reach. And they're all right where you'd expect them to be. Where you would look most often is the stuff you want to see most often. And the stuff you want to see less often, further away. Stuff you would want to see when you're looking straight ahead is there, and down, and so forth. That's not something that anybody designed in any program. I know that Howard Hughes was a massive micromanager, and he spent countless hours in that cockpit needling his engineers to move this and change that and put it over there. But the end result is amazing. That is one of the most intimate cockpits I've ever been in, and I wish it were a flying aircraft so people could have the experience of what it's like to run an aircraft of that size. You have no sense of the size of that aircraft when you're in the cockpit. You feel like you're flying any other plane. Yet you're sitting in this gigantic behemoth of Douglas fir or whatever it is that they built it of. So a very important lesson learned is that the intimacy of the cockpit, which I believe is critical to being able to pilot that aircraft gracefully, is more than just mere. You got to be able to sit down and go, oh, I like that cockpit. Now this one that I'm sitting in right now, I pretty much have that feeling, but I wish it were about 4 inches wider. And I'm sure there's some people much bigger than me that would say, well, I'd like it about 6 inches wider. I probably should have run the cockpit out the full width of this center section, all the way out to the 30 inches. But there were some reasons why I didn't do that have to do with structure that's inside the wing. And with a little bit of work, I could redesign that, and I could probably build a new pilot's cage and modify this center section and get a little bit more width. But why go to all that work if I'm not even sure the aircraft's going to fly properly? This is good enough for now. My buddy Bob complains about, oh yeah, I can't use safety pins for a connector here. You got to have the circle clip and feed it through there. I know. That's what you need for regular flight safety. But we're in ground testing, so it's good enough for now. And that's how I approach this whole thing. And little by little, we'll jack this thing up to it's good enough for now and way off into the future. We'll get there eventually. So here we are, and I'm set up today. I got both harnesses on because we're going to get the sawhorses out of here in a minute, and I'm going to give you a little demonstrations. You'll see behind me here, I have some nice barbell weights strapped on the back, and you might be thinking, gee, Rob, what'd you do? Get the weight and balance wrong? And you built this really lightweight aircraft and then you strapped 20 pounds onto the back end? And no, that's not the case. Because we don't have the wings mounted here, the cockpit is really nose heavy. So I've put enough weight back here so that when I actually lift the center section like this, it lifts just like it will when the wings are attached. It's not as heavy. This whole thing weighs about 40, 45 pounds like this. But it gives me a fairly good simulation of what it's going to be like to run with this thing. And that's probably the last thing I want to cover. I'll tell you one more funny story. I'll put up a picture of my original wing here, and you'll see me taking off on the very first flight in this picture. And it was really quite hard to get there. And you might notice I'm sitting a little low in the wing. And that's because I designed the whole thing up, and I had a seat in there, and I was using technology out of the, probably the 70s. On pilot suspension system, I was using a swing set seat, much like they used in the Icarus II, Icarus V. And, well, I have to admit that I built the whole thing, designed it, built it, got all the components put together. We take it out to test flight, and I never, ever, prior to that, tried to run with it. How dumb is that? It's really dumb. I just assumed it was going to work. That's a bad plan. You know what happens when you assume. So, on that aircraft, when I tried to run, the seat went whack, whack, whack up against the pilot's cage. And it was hanging up on the tubes. It was a disaster. It was really bad. Needed a soft harnessing system like this, which is what I rapidly ended up with after that first little flight. So, I've learned my lesson, and I've been practicing here in the backyard of picking this thing up and running with it to see if I can actually do it. And besides, I'm not nearly as young now as I used to be then, and I can't have anything getting in the way or binding or preventing me from waddling my way into the sky. So I'm going to be picking this up and setting it down, and then we're going to come back and we're going to talk about some of the ergonomics involved with lifting an aircraft that's 108 pounds. So stick around. I'm going to flip you around. We're going to come back and we'll talk about that. Okay, well, I'm back in the aircraft here. Now, I haven't strapped into the suspension system because I want to be able to maneuver around easily for this particular little segment. So I'm going to stand up here into the lift harness, and I'm going to lift the glider up and over, at least the center section. I'm going to move over here where I hope you can see me and set it down. Now, here I am on the ground. And this is to be the normal position that I'll be in prior to standing up to launch the glider. And let me tell you, even though this seems like a very simple little situation, it's really quite complex because of the human ergonomics. Once again, that human-machine interface. And originally I had a much smaller wheel up front. The wheel that's up front here used to be in the back. And when it was down on the ground, my legs were in such a position, I literally couldn't pick the glider up. It was like I was bolted to the ground. I could not move. And that's because this leg here was not in a position that allows me to generate any leverage to do the lift. And it was strictly because this pilot's cage, the lift harness, the whole setup didn't allow my body to be in a position where I could get sufficient leverage to actually stand up with 108 pounds on my back. This pretty much solves this problem. I did some testing with the lift harness with weights on it, weights that simulated the weight of the aircraft, and practice indoors standing up and going, where does my body have to be in order to do this job? Because I'm no Hercules, and a lot of other pilots aren't either. And I got to design this so that the average schmo out there can lift it up. And this is what you end up with. You have to be enough height off the ground so that you can get this leg at 90 degrees and get a foot underneath you for this type of aircraft. And that allows me to literally push with my right foot, just like that, and lift it up. And now I'm in a flying position. I can move a hand down here on the horizontal. I'm close to the flap handle. I can operate that. And nominally I would be hooked into the suspension straps, which give me enough balance to where I can actually grab the flap handle and just let it hang on the harness, and I run the control stick over here. And it gives me enough control over the control stick for the launch. And then on landing, well, you're a little hunched over like this, and you flare, and you come in like this, and you got your little run to land, or you try to bring in a full stall and just stop like this. But then you got to set it down. And when you set it down, it's the reverse situation. You have to have a system where you can put one leg back like that, fully folded, and the other one 90 degrees. It's the only way you're going to be able to get the aircraft up and down without help. So that was another thing that I had to sort out on the design. And probably, you might have been able to do it in very high-end human-machine interface software, maybe. I'm not exactly sure of that, because I don't know how that software would actually simulate this whole harness system. And the feel of the harness. The harness is not free everywhere. There's some binding and so forth that limits how much you can move. It's a tricky little problem to solve. So you see how I can now lift and set it down. I think I've solved that problem. And next, we have to find out, can you actually run with the darn thing? And I'm going to reset here, and I think I'm going to be able to give you a little demo of what that's going to be like to run, to take off and land. So stick around. We'll be back in a few minutes. So there, we see it took me a little while to get going. Once you're hooked in everywhere, both in suspension and lift system, it does restrict your movements a little bit. I'm going to go back. Reset. I'm going to lengthen the leg strap slightly, give me a little bit more freedom of movement. We'll see what happens then. Well, that definitely felt better. I don't know what that's going to be like with the whole wing there, and 108 pounds. I just hope that there's a nice headwind. Let's see what it looks like going the other way. So there we go. I'm a little out of breath already. Just a few runs, and it's got me a little winded. Of course, I'm not young anymore, but this goes to show that, well, designing an aircraft is one thing. Actually, I should back up one more step. Conceiving of an aircraft, dreaming about, that's one thing. Many people do that. Designing that aircraft so it can be built, that's another whole thing. Building it, that's another whole thing. And then making it actually work in real life, wow, that's another whole thing too. So, long road, people wonder why this takes 10 years. You know, you raise a family, you work in your garage, it takes some time. But I'm going to get it done. And thanks to the support of all my patrons and those folks who follow on YouTube, you're going to make it possible, and I really appreciate it. Hang in there with me. We have a little pause here in the development of the glider. I've had to go out and do a little contract job, which I'm taking a break from today, but that's absorbing most of my time, and that job should be done in about 3 weeks. Then we'll get back to testing. And keep your fingers crossed. The next time I run with that center section, hopefully the wings will be attached and I take off. So until then, I'll say fly safe and bye for now.